Here we are going to discuss about the theorems to calculate the moment of inertia. And the first theorem is perpendicular axis theorem. And the perpendicular axis theorem can be applied only for the 2D or planar bodies. This important point you need to keep in mind, that this is applicable only for 2D bodies or the planar bodies. Like for example, we can apply it for the disc, for the ring, for a rectangular sheet, etc. Right? Okay. Now let's discuss the derivation of this perpendicular axis theorem, and then we will write down the statement of this theorem and the equation of this theorem. Right? And here I have taken a example. This is a rigid body. This is a rigid body, and this is the side view of this rigid body, where x-axis and y-axis are passing through this plane of this body, and z-axis is perpendicular to this body, a plane of this body. And if you look from the top view, this is the x-axis and this is the y-axis, and they are passing through the plane of body, and z-axis is perpendicular to that. Okay. Now let's find out the moment of inertia of this body about the x-axis. Let's find out the moment of inertia of this body about the x-axis. Now because it is a continuous mass distribution, mass is distributed on the complete surface like this, right? So what I will do, I will take an elemental mass, I will define the moment of inertia for this elemental mass, and then I will integrate the moment of inertia for that elemental mass. So I have taken a elemental mass. This is a elemental mass. This blue mass is a elemental mass, and let's assume that the coordinate of this elemental mass are x comma y. Okay. If you look in the top view, so this is x-axis, this is y-axis, and this will be, from the x-axis, the perpendicular distance will be the y coordinate, right? If this body or the surface is the planar surface, right? And the perpendicular distance from the y-axis will be the x coordinate for a body which is lying in the xy plane, right? Okay. So now let's define the moment of inertia of this elemental mass. So can you tell me the formula for the moment of inertia? That is r square dm, right? We are calculating about x-axis, right? We are calculating di, the moment of inertia of elemental mass about x-axis. So in the formula, r square, r is the perpendicular distance, and we know for this elemental mass, if the coordinates are x comma y, then y will be the perpendicular distance. So instead of r, I can write down the y. So dix, okay, dix is y square dm. And if I ask you what is the total moment of inertia about x-axis, ix, you will say that is the integration of dix, and that is integration of y square dm. And because we are deriving the theorem, so we are not going to put the limits, we are not going to substitute the limits. Okay, we will keep it like this only. Okay, let's call it as the equation 1. So we got the equation 1. Let me just highlight it. So this is our equation 1. Okay. Now let's find out the moment of inertia of this surface about the y-axis. About this axis, I want to find out about this axis. So again, I will apply the formula diy. I will calculate the diy, and the formula will be r square dm, where r will be the perpendicular distance from the y-axis. Okay. So let's find out diy, that is r square dm, and we know that the perpendicular distance is x coordinate. If x comma y is the coordinate of the elemental mass, then x will be the perpendicular distance. Okay, so that is x square dm. Okay, so iy will be, okay, my writing is not good. but still I think you can understand what I am writing down. So diy is integration of diy, that is integration of x square dm. Okay, very good. So this is our second equation. Let's call it as equation second. And now let's define the moment of inertia about z-axis. So to calculate about z-axis, we need to first calculate the perpendicular distance of this mass, elemental mass. We will calculate diz and then we will integrate that. Okay, so this is the elemental mass. You need to look in the side view, then you can understand it better, right? Or even you can look at the top view. So this is the perpendicular distance, right? This is the perpendicular distance. If you look in the top view, it's like this. This is the perpendicular distance. And this perpendicular distance, can you tell me what is that? That is under root x square plus y square, isn't it? Yes, yeah. So if I take the elemental mass and define the perpendicular distance for that elemental mass from the z-axis, so that perpendicular distance will be under root x square plus y square. So if I calculate di about the z-axis, so that is r square dm, so that will be x square plus y square dm. If I calculate iz, that is integration of x square plus y square dm. Okay, so this is iz. Now let me rewrite the iz again. So iz is okay, yeah. So iz is, I'm just opening the bracket. So integration of x square dm plus integration of y square dm. Okay. Now can you tell me what is x square, integration of x square dm? From the equation second we know that is iy. What is integration of y dm? From the equation 1 we know that is ix. So I can state that the iz is equal to iy plus ix, or let me rewrite it, iz is equals to ix plus iy. Okay. One important thing I am going to tell you now. This is our formula for this perpendicular axis theorem, or this is the result of this perpendicular axis theorem. Now you need to keep in mind that the z-axis is perpendicular to the surface. X-axis and y-axis are passing through the surface and they are perpendicular to each other. And x and y and z-axis are passing through one point. Okay, this is the condition, right? I am writing down iz. Doesn't mean that if anywhere z-axis is there, I can rewrite this relation like this. Okay. For example, if I consider like this is the ring and I say that this is the z-axis, the diameter is z-axis, another diameter is, let's say, y-axis, and the another is x-axis. So I cannot say iz equals to ix plus iy. You need to keep in mind z-axis is perpendicular. Here we have taken a perpendicular axis, right? Z-axis is a perpendicular axis. Now it can be anything. Okay, I can name it as x-axis, y-axis, or x-axis dash, y dash, or anything, right? But that should be perpendicular to the surface. And the x and y-axis are perpendicular to each other. They should pass through the plane. Okay. So now let me write down the statement. So I can say that according to perpendicular axis theorem, moment of inertia of a planar body about an axis passing through the perpendicular of passing perpendicular to plane of body to plane of body is equal to sum of moment of inertia of the two perpendicular axes passing through the same point and plane of body, right? So let me give the in general names. So let's assume that this is a planar body. Okay. Yeah, this is a planar body, and this is, let's call it as axis A, axis B, and the third is perpendicular to this surface. Okay. Third is perpendicular to this surface. Okay, let's call it as C. Okay, let me name them. So this is X, Y, sorry, okay, A, B, C. So I can say IC equals to IA plus IB. Now in the next we are going to derive the second parallel axis theorem. These theorems are important to calculate the moment of inertia, and we will also learn the application. No need to worry about that. And if you don't know about the moment of inertia, you can watch the previous lectures, go through them. You have the full playlist